This is the second lecture on hybridization. In this lecture, I'll be reviewing expanded octets. These are the central atoms that have more than 8 electrons, more than the octet rule. And we'll look at the type of hybridizing that occurs to achieve central atoms beyond the 8 that we're so accustomed to hearing, that octet rule. And understand this. I understand that there's a lot of work being done that show that the current hybridization stops at sp3. We have learned previously in another lecture sp, sp2, and sp3. And I'm going to take you to two more hybridized electron domain structures. And I understand that there is a lot of work being done out there that has shown that the d orbital does not hybridize. But I'm going to continue on with this lecture so that those people that are being taught that d is involved, okay, have that background regardless. Okay, so I say that as a disclaimer. Okay, so let's getting back to business here. Noticing that I have the methane molecule here, and in this methane molecule, I have each hydrogen bringing one, each carbon bringing one, and we can say that this carbon, by sharing 4 more electrons with its valence shell, achieves a stable octet. And if you notice, carbon is in the second row of the periodic table. In the second row, we only have s and p orbitals for a total of 8 electrons, 2 in the s, 6 in the p. So once you achieve the 8, you're as stable as a noble gas. And that's where the octet comes, because we deal with a lot of that. But when you're in the third energy level, right, the second energy level has 2 sublevels, and you've learned in the third energy level, you have F, S, P, and now D. So the third energy level, because there are d orbitals there, whether there's electrons there or not, okay, we have a total of 18 electrons. Now, it doesn't mean that they're going to have 18 in here. What it means is that we can incorporate some d sublevels in our mixing, in our hybridization. So what I'm showing you here is something called sp3 hybridization. And as I previously have shown you, this is review, with some energy, this electron, oops, not a core electron, this 2s electron jumps out, and of course the arrow would go up to show the same spin. Okay, I guess I can try to get that done. Let's leave that there for now. Okay, so we got 4 orbitals. We have a what? We had an s and 2 p's, and they mix together to give me 4 equal energy levels of the same size, which repel themselves into this tetrahedral electron domain geometry, allowing this side of the orbital to bond and allowing this side to bond at different places. This is not a p orbital. This is an sp3 in all directions. And of course, they repel themselves into a 109.5 bond angle. Okay, we can have lone pairs, we can look at the geometry. But in all those cases I've shown you previously, we have 8 electrons as the max. Let's go on and see some examples of an expanded octet and its hybridization. So here's phosphorus. And if you notice, I have phosphorus loves to bond with chlorine and does so in this arrangement. So what you have is a P bonded to a Cl, bonded to another Cl, and we have 3 of these kind of planar molecules in the middle. Now, of course, if I'm drawing this correctly, the Cl's will have all their dots, lone pairs. You got to draw lone pairs when you're drawing Lewis dot diagrams with the dashes like this. You've got to show that. Now, of course, this dash is a pair. So now we have 5 pairs of electrons, and we know that the bond energies of all of these are exactly the same. Yeah, yet we have different orbitals involved. That's tough to understand because different orbitals have different energies. And we know that this bond angles are 120 and 90. And because the bond angles are 120 and 90, we can't explain this shape with this empirical evidence other than trying to say that these mix. So what happens? Well, what we think is an electron from the 3s gets excited, jumps to an empty orbital. I understand this orbital should go up. And of course, now we have 1, 2, 3, 4, 5 orbitals mixing together. An s, 3 p's, and a d mixed together to equal 5 equal orbitals of all the same size and energy, same shape and same energy, that can repel themselves into this shape. In this shape, where you have orbital up and down, these are the axial orbitals, and then you have that trigonal planar in the middle, tough to draw, okay, is something called trigonal bi-pyramidal. A triangle bi-pyramid. Okay, and it's tough to draw, but what you're going to have is that trigonal planar in the middle, and you have axial positions on top and bottom. And that's where you get the 5. It's a top of a 3-sided pyramid on this side, top of a 3-sided pyramid. And the electron domain geometry is also always trigonal bi-pyramidal. The molecular geometry is where the atoms exist, and of course that's trigonal bi-pyramidal. And again, to get a good feeling for this, look at my lecture where I take the balloons out and put 5 balloons of equal size, and they repel themselves by VSEPR theory, valence shell electron pair repulsion theory, into this shape, this most stable shape for 5 equal pair of energy electrons. Okay, now electron domain geometry for this type of hybridization, which is called Sp3D, right, we incorporated a D, is always going to have these bond angles. They always have electron domain geometry of the trigonal bi-pyramidal, which sounds smart. You should just drop that name when you're trying to sound smart. And the molecular geometry in this case is going to be the same because the atoms are in that position. The molecular polarity, there's none. This is a very symmetrical shape. Okay, the trigonal planar arrows would cancel, and these two arrows would cancel in terms of dipole moments. Very symmetrical. All the dipole moments would cancel. But we have more shapes in this family. Let's go see. So here we go in the trigonal bi-pyramidal family. Okay, there are 5 electron domains. That means there's 5 equal shaped orbitals, which we need to have if we're going to follow the VSEPR theory, and electrons are going to find stable shapes, okay, which is the least amount of what? Restrictive forces between them. Minimize the repulsions. They find the most stable state. Now, bonding domains, there's 5. There's 5 places. There's 0 non-bonding domains, which means there's 0 lone pairs. You would have a trigonal bi-pyramidal molecular geometry. And that's the example I just drew for you. So trigonal bi-pyramidal means you have a triangle. This is nice. It's a planar model. Triangle on one side, triangle on the other. So it's a bi-pyramid. I should say it's a pyramid on one side, pyramid on another. Okay, so it's a cool name, trigonal bi-pyramidal or triangle, both sides, pyramid. Okay, now, if we have one lone pair, now it's important to understand in this shape, this VSEPR shape or this hybridized shape, with one lone pair, we make a seesaw shape. And it's nice to show this with a molecular model. I can't do this on paper, but one lone pair, that lone pair is going to be in the equator position. There's 4 bonding domains, SF4. And as we roll down here with 2 lone pairs, it means 3 bonds being made, CLF3, it's a T shape, that's easy to see. Don't forget the electron domain geometry is a geometry of where just the electrons are. So it's still 1, 2, 3, 4, 5 trigonal bi-pyramidal for all of these. And of course, if you have 3 lone pairs, and again, where the lone pairs will always be in the equator position, and the answer to reason that is, the answer to that reason, I guess, or that question, is because that is the minimum amount of strain. 120 bond angle, okay, between these 3, it's easier than the 90 you would have if they were otherwise. So again, they minimize their strain or they find the most stable position for the electron-electron repulsions as a triangle here. So this is where that happens. So you have essentially 4 shapes here. If they're all bonded, they're trigonal pyramidal. If there's one missing, it's a seesaw. And it's easy to see the seesaw. If you lay it on its back, this will go rock back and forth. Again, look at my videos with the balloons. You can see that. This is a T-shape, obvious reason. And of course, this molecule is linear. All right, and that's the Sp3D family, as I have talked about. Now, just to review, we have some other families. We have the linear family when you're a central atom, and this is always linear when you're sp hybridized. This is the sp2 family, and you have 2 shapes. Molecular geometry is always trigonal planar. That's the middle. Remember, this is the middle of the what? This is the middle of the trigonal bi-pyramidal, that triangle there, that trigonal planar. And trigonal planar is for sp2 hybridization. And s and 2 p's mixed. With one lone pair, it's angular or bent. And then if you've got 4 pairs of electrons surrounding the central atom, this is sp3, and s and 3 p's mixed. to give me 3 equal orbitals. And there are 3 shapes. If they're all filled tetrahedral, 1 lone pair, top of a 3-sided triangle. And if you've got 2 of these, you've got these bent shape, which is the legs of a tetrahedral. Okay? But they're all, remember, this electron domain geometry is the same throughout, where the electrons are. If I ask you for the molecular geometry, it's where the atoms actually exist. Okay, so we got one more, and we're going to head back to the next and last of the hybridizations. So before we go on to the last type of hybridization and the VSEPR major shape, let's step back and redo this one from scratch. So we had PCl5. So what I'm going to do here is I'm going to take phosphorus. I'm going to put its 5 valence electrons. We should know it has 5. And then I'm going to write the chlorine. I'm going to write its valence would be 7. And we are building a Lewis dot diagram structure. Notice I'm putting in the lone pairs for my chlorine. And you can see by sharing that this phosphorus feels like it has 10 electrons, which breaks the octet rule. And the reason why it breaks the octet rule is because phosphorus is a third row element. I'm sorry, a third period or row element. Okay, so because phosphorus is n equals 3, or the third energy level, okay, it has 3 orbitals, s, p, and d. So because you have more orbitals beyond the s and p, there's more opportunities to make more covalent bonds. Now, of course, the explanation, as I talked about, is phosphorus being 3s2 and then 2p3. Okay, if you put the s's in, and it's important you understand the basics here. With some energy, this electron is excited to a d orbital that it does have, even though there's no electrons there. I'm sorry, this is 3s2, 3p3, and this is 3d, and it jumps to the 3d. And now you've got one of the s, you've got 3 p's, and then 1 d. So this becomes an sp3d orbital. What it means is an s plus 3p orbitals for this dumbbell shape, plus a d orbital, which I'm not really good at drawing, but one of the shapes kind of looks like a pacifier, the ring around. You put these together, and what you get is you get something that resembles, okay, a sp3d orbital, and I would draw this 5 times. 5 equal shapes. Now, it's important you understand these are 5 equal shapes. These are all sp3d shapes, and there's 5 of them. Because they're the same size and same energy, they will repel themselves into a top of a 3-sided pyramid on both sides. So if I draw this again, here's the phosphorus, okay, here's my first Cl, here's my second Cl, and then you're going to have, let's go backwards a little bit. This one will go into the board, Cl. This one will come at me. So it starts thin and gets bigger. There's a Cl, and this will be on the same plane. So that shows me, not very artistically correct, or artistic, but it shows me that this Cl here is a triangle planar, and this is a trigonal bipyramidal family. Okay, 1 lone pair is a seesaw. This is a lone pair, you get a seesaw. 2 lone pairs are T-shaped, and notice the lone pairs would be on the equator positions because of strain. Go over your shapes with that worksheet. Okay, and that's how you start from scratch. So let's go on to the next one. So the final and last VSEPR type of shape, major shape, denoted by the type of hybridization, okay, it would be something like this compound, which would be S-sulfur hexachloride. All right, notice the sulfur in the middle, and notice if we count pairs of electron, 1, 2, 3, 4, 5, 6, we have 6 pairs of electrons surrounding the central atom. That's 6 bonds of the Cl's. Now, of course, if I'm drawing this, I have to make sure I write my lone pairs. So if I want to be dashing again, lone pairs are necessary, unbonded electrons to show them. So now I'm more correct. Now, 6 pairs is different than the 5 pairs. And you might ask yourself, well, why is this the last one? Well, eventually, negative balloons or lobes or sp hybridized orbitals, there's only so many you can put in close proximity. They repel themselves into these stable shapes that we're talking about. They get into the most stable shape with the most minimal strain between them. So they repel, but they find the position of the lowest energy. Well, if you keep adding more of these, the energy level, because of proximity issues, starts rising so much that this compound just won't be stable. So 6 is the magic number, or the limit of how many pairs of electrons surround an atom, at least that we know about. Now, before we get to that discussion, how does this all occur? Very similar. We can add some energy. So maybe the 3s2 goes to a 3d, and maybe this one goes here. And I say maybe because this is all a theory. And of course, these arrows would turn up and be in the same plane. Okay, but I'm limited by the program here. So by some energies, this configuration gets excited, and now we have an S, okay, 3 P's and 2 D's getting together, and that's your hybridization. So they all mix, and all the orbitals have the same energy level. The bond energies of all of these are the same. We know the shape already from experimental evidence to be an octahedral, as we call this. So the molecular geometry and electron domain geometry is called an octahedral. And the reason for that is because there are 6 sides. Tough to draw, but again, if you look at the balloon lab, or the balloon demo I did by blowing them up, that you should look at, you can see how this model looks like a octahedral. Now, why? Well, essentially you have an axial, this would be the sulfur. Then you have basically a plane square and X in the middle. And if you think with me, this would be one triangle, this would be another, one behind, one in front. We take 4 triangles to fill the top up, and if you flip it over, the same 4, so there's 8 sides to this. Okay, but this is octahedral. And as every unique hybridization has octahedral, okay, has its own unique shape, there it is. So we're an octahedral family. Okay, the polarity is nonpolar, very symmetrical shape. The bond angles here are going to be all 90, okay, all 90 degrees to each other. And one way to look at it, let's go back to the tables, and I'll show you this, all of its other related shapes with lone pairs. Okay, so here's our shapes. Again, it's nice to see the balloons live in person, or the video I made, but these work pretty good. Notice the planar square in the middle, or this X, or you want to call it in the middle, and you have these axial positions. Now, the electron domain geometry of Sp3d2, right, 1s, 3 P's, and 2 D's makes 6 equal size orbitals that repel themselves by the VSEPR theory into an octahedral position. If you have 6 things like SF6 or SCl6, it'll be an octahedral for the molecular geometry. Molecular geometry is where the atoms are. Electron domain geometry is where the electrons are. In this case, they're the same, because there's atoms where all the electrons are. But with one lone pair, electron domain geometry is still octahedral because it's still Sp3d2, but now it's a square pyramid, the top of a square pyramid. That's why it's called square pyramidal. With 2 lone pairs, and notice the lone pairs in this shape are in the axial positions. Just by steric strain differences alone, we find that the lone pairs want to be in these positions. And of course, with 2, this is, you have that square in the same plane, it's square planar. And here are some examples. This, of course, is 6 electron bonds, 5 and 4, and these are how many lone pairs. So these are the family. The family's octahedral. It's Sp3d2. We have 3 molecular shapes. We only have 1 electron domain shape. Okay, notice the lone pair is in the axial position, but in the Sp3d family, which is the trigonal pyramidal one, okay, we have 4 shapes. So Sp3d, we have trigonal pyramidal, 1 lone pair, seesaw, 2 T-shaped, 3 linear, but the lone pairs in this case, unlike the one I just showed you, Sp3d2, the lone pairs for Sp3d, Trigonal Bi-Pyramidal family, drop that name, is in the equator positions. So something you have to take care of. So that represents it for the two types. And of course, if you go back to where I was, this is an expanded octet as well, because sulfur by sharing feels like it has 2, 4, 6, 8, 10, 12 electrons. So 12 electrons are being shared. And of course, that busts the octet rule. Why? Because sulfur, N equals 3. It's in the third energy level. Okay? Row 3 on the periodic table is not bound by the 8. That doesn't mean sulfur is always going to have 12. It just means that it can have 12. A lot of our Lewis dot diagrams will still work for 8 because there's something about filling the S and P, as I've talked about. So what I want to do now is I want to model a couple of different questions that I did in class. The homework is going to be an expanded octet homework worksheet, and I want to just model a couple of these. So let me continue. So this lecture follows up this worksheet. So let me model PF6 -1 here. Okay, so we have phosphorus. It has 5 valence. 1, 2, 3, 4, and 5. But this negative here means I have to add 1 more electron. So I do. Then I have 6 fluorines. Lone pair, writing is fun. Put the 7 valence electrons and put the lone pairs around. You'll say, Mr. Grotsky, are you really going to count these? You bet. For bananas, I will. F. Okay, and then another F. And you notice that, let me just write here, that this guy is sharing an electron that came from the environment. Doesn't matter. But this is the correct. Now I can draw this another way to make sense. I have phosphorus making 6 bonds. So 1, 2, 3. I'm kind of using the structure in my head. Hey, 6 bonds makes this to be Sp3 hybridization. So the F's would be on the plane. There'd be F in the axial position. And of course, to do this correct, I have to put the dots in. Now, of course, I'm just asking for electron pair geometry here. But I'm just saying you could do this Lewis dot diagram this way. Just make sure you put in your lone pairs. And you get the point. I just want to be accurate here. All right, so this is the same thing, and you can clearly see that this whole thing had an electron added to it, so we draw brackets to be polite and say the whole thing is -1, which makes the polarity non-applicable. If you're an ion, it's a polyatomic ion. Whole thing's -1, so it can't be polar. Polar and nonpolar are basically a discussion for things that are covalently bonded. This is now, I know it's covalently bonded, but now it's an ion. So now it would be an ionic compound it would be part of. Asking the polarity or non-polarity of something that's an ion is like asking number 5, what's its marital status, okay? So you don't do that. So the electron pair geometry, because it's got 6, is of course an octahedral. Molecular shape is the same thing because it has atoms in all positions and its polarity is not applicable. All right? Let's go down with, because people like when I go out of order, to XeF4. I have Xe, and I put in the 8 dots it has. I think the track team is running up and down the stairs. Okay, now, I'm going to put in my Fs, and I'm putting 4. And I put in its 7 valence, and I'm off and running. Okay, now I'm going to just for fun figure out where my pairs of electron. Here's 1, here's 2, here's 3, and here's 4. But wait a minute, I got more here. There's 5 and 6. Yeah, there are 6 pairs. There's 2 lone pairs. Okay, so it's like Raj made my video with the announcement. So I could draw this another way. Xe in a darker color, and the same idea. Now, where are my lone pairs in the octahedral family? This is an octahedral, right? Because there's 6. I'm drawing Sp3 How do I know? It's 6 orbitals, 6 pairs. 1, 2, 3, 4, 5, 6. By having 6 pairs, I know it's this hybridization, which means I'm in the octahedral family. Now, where are my lone pairs? As you've learned, the lone pairs are in the axial positions. So we've got that square planar thing working. And then shapes do make sense. They really do if you think about what the name represents. This is a square in the same plane. So this is a square planar. If you need to look at your worksheet for the shapes, please do so. And this molecule is nonpolar because these 4, if I look down on it, I'm going to have 4 different what? Dipoles. And the dipole moments would go from the negative, the partial negative, to the partial positive. Or I should say the positive always points to the negative, sorry. So you always have a flow of charge to the more electronegative atoms. So I've got 4 vectors of equal size and opposite direction. Of course, they cancel themselves out. This is a nonpolar molecule. All right? So that's how we do it. Okay? Remember, the ones with a negative charge, you have to add an electron. And notice their polarity is non-applicable because they're ions. So please try the rest. I have the key, and good luck.